so on and so forth. This is the first time that I'm seeing this address. This is the first time I'm seeing this address. So these are all compulsory or cold start misses. So once, but if I see the address again, then I cannot classify it as compulsory or cold miss, irrespective of after how long I see the same address. This will not be a compulsory or cold miss because you have already seen this address. Then we saw something called capacity misses. So the capacity miss definition makes sense only in a fully associative cache because there can be conflicts in a set-based associative cache. Let's say I take the example of these two blocks and these two blocks. I have made it into two sets. I might bring a block here and kick out a block here because in this particular set, there was no space. But as a whole, the cache might still have space, which I'm not taking into consideration. So in this particular set, there is no space, so I kicked out. So this is not a capacity miss. Capacity miss is when the cache utilization is full. Then only we can define a capacity miss. So capacity miss is defined in a fully associative cache. It means that there is no space, so that's why you kicked out a block. If the CPU generated the address again, then it's called a capacity miss. Conflict misses, there is space in the cache, but you see maybe all addresses are going into the same set. So that's why you are kicking out a block from the particular set. That's why it's called a conflict miss. This particular B3, this particular B1 is a conflict miss because you first stored B1 here, B2 here. Then when B3 came, instead of finding out these two locations, since it belongs to this set, I removed this B1 and placed B3 here. Now, if B1 was requested, if B1 is requested again, it's a miss. So, those misses that are misses but not misses in a fully associative cache are called conflict misses. The fourth C is coherence miss. As I said, we might not be seeing that in this class. It is predominant in multi-core processors where we share cache among, maybe there are private caches and shared caches. There's a way to deal with all these misses, but I hope the general idea of what is a miss and what are the different kinds of misses is clear to you. If you are not understood, please ask me any question. I will be able to answer, at least till now. If you can answer the poll, it will be great. Okay. Okay. So now I decide. So now we will go to the next step. What we are asking is, so let's say I have the CPU, and now we will work on a problem where we are using a fully associative cache. But of course, the same is applicable to the set-based cache also. But let's say it's a fully associative cache, and I have 4 blocks. So there are 4 locations that I can store the cache block. It's a fully associative cache. I'm not writing the tag anymore. I'm assuming that you are searching for the tag. And then there is this main memory. Right. So the eternal question is, let's say I have the CPU has generated an address B1 followed by B2 followed by B3 followed by B4. Now I am talking about block addresses, but I'm just talking about block addresses, but the CPU will always generate an address for a byte. It's a byte addressable memory. Of course, it can request for more bytes, but it will generate a byte address. Right? Might say, I want these many number of bytes from this particular byte, but I'm just writing a block address so that it's easier to visualize. So then it generated an address for block 5. So I stored B1 here, B2 here, B3 here, B4 here. Now, so these all 4 were compulsory misses. All 4 were compulsory misses or cold start misses. This is also a compulsory miss. This is also a compulsory miss. Now, when I brought back B5, where do I store B5? So the question is, where do I store B5? Should I store the B5 in this location, in this location, in this location, or in this location? This is called a cache replacement policy. So what a policy that I use to remove an old block and store a new block is called a cache replacement policy. So we want to design a cache replacement policy which is effective. What do I mean by effective? Let's say, let's say I could look into the future. Let's say I can look into the future and see that B2 will never be accessed. I somehow was able to look into the future and realized that the CPU has never requested for B2 anytime after this. Then what will you pick to keep B5?
B2.
B2, right? So anyway, I have to keep, because I know that B2 will never be used again. So I will just remove this and place B5 here. But as you know, I cannot look into the future. So I don't know what will be accessed here. So I don't know in the future. So this is a time of access. So I don't know what will be accessed next. So which means that I should make an informed decision of what I should remove. So what will you remove in this kind of accesses? Anything that you can come up with?
B1.
Why are you saying B1?
I try to keep the most recently used stuff.
Yes, so that's the general policy that most of us think about. It's called least recently used policy. So which was the least recently used, I will remove that block. In this case, the least recently used block is B1, right? Because this was the farthest in the timeline. If the accesses were something like this, let's say the accesses were B1, B2, B3, B4, B1, and then B5. So these four were misses or compulsory or cold start misses. This is a hit, right? Because I already find it in the cache. So this is a hit, but this is again a miss. This is also a compulsory or a cold start miss. But I will not remove B1 anymore because I know that when I look back into my past, I know that B1 has been the most recently used. The least recently used is, in this case, it is B2. The least recently used is B2. So I will remove that and place B5 in the position of B2. So I will remove B2 and keep B5 here. So this policy is called least recently used policy. Of course, you can come up with any policy you can think of. You can come up with a policy called MRU, which is most recently used. I will say, no, I don't want to pick out the least recently used block. Let it be the way it is. I will implement the most recently used policy, which means that I will remove a block which was most recently used. In this particular case, I will remove B4 because that's the most recently used. In this case, I will remove B1 because that's the most recently used. So I can come up with an MRE policy. Or I say, I don't want to have the headache of all the doing this. I will come up with a random policy, which means that I will just toss a coin or I will just generate a random number and do a modulus by 4. So I will get either of the 4 addresses. I will just do a random number generator and I can do any crazy stuff I want. So it's just a random policy. I'll pick a block in random and just remove that block and keep the new block there. So it's just called a random policy. So I have come up with an LRU policy, MRE policy, and a random policy. Any other policy you can think of?
Maybe least used.
Yeah, least recently used we already saw it.
Not least recently, like the least used data. I mean,
Least frequently used.
Okay, oh, excellent. So what you are saying is, so how do I know how many times I have used something?
maybe I can keep a counter for
So,
every
so where do you keep the counter?
in this tag only.
Okay, so now what Aditya is saying is we will come up with a replacement policy which has something like this, but each one will have, along with the tag, each one will have a counter, right? So I will have a counter with 4 blocks, and then I have the main memory. So let's say if the CPU generated an address for B1. So now I stored B1 here. So do you want to increment the counter or decrement the counter?
Increment.
So okay, so I will increment
I
the
mean,
counter.
override it with 1.
So override it with 1 or
Because
increment.
this is the first time I'm fetching B.
Okay, let's for okay, okay. Okay, so let's say okay, before that, how many bits do you want to have here?
I mean, 8 bits can be fine, I think, because like the number of times we use some particular thing won't exceed the limit.
How do you know that?
By experience, I think so.
Are you sure that you will be using my block only 256 times?
Maybe then 16 bits can be fine.
Then
I mean,
I'm saying then I'm wasting 2 bytes per block, right? So let's say I have an 8 MB cache. Then do you know how many blocks are there in 8 MB cache? See, let's say my block size is 64 byte. The cache size is 8 megabytes. How many blocks are there? Can anybody calculate how many cache blocks are there here? How do I calculate this? The block size is 64 bytes. Cache size is 8 megabytes. How many blocks are there in the cache?
128.
2 power 3 into 2 power 20 divided by 2 power 6. Right? Yeah, somebody should say the answer. What is the answer?
No, sir, I thought KB. Sorry.
Yeah, can you please take a pen and paper and work this out? I know, as I said, I know everybody is extremely smart, but please tell me the answer for this. How much is 2 power 17? So how do I calculate that? I just do 2 power 7 into 2 power 10, right? So 2 power 7 is what? Come on, yeah. Okay.
So 1,31,000.
Pawan Kalyan?
Yes, sir.
How many blocks, sir? Did you understand the question or were you following the question?
Yes, sir.
Yeah, so how many blocks are there?
2 power 7 into 2 power 7 kilobytes.
Yeah, 2 power 7 into 2 power 10. So what is 2 power 7? 128 kilo blocks, right?
Yes. Yes,
So
sir.
if for 128 kilo blocks, if I add 2 bytes, how much will be the memory overhead?
Sir?
So Aditya said he wants to use 2 bytes per block. So if I have to have 2 bytes per block, then I have to add 2 here. Right, so I am adding 2 bytes per block. So what is this? It is 2 power 9 into 2 power 10. So how much bytes am I adding as extra?
Extra
How much?
to 128 KB extra adding. We are adding extra
No, not
128.
128 KB. I'm not actually adding 128 KB. I'm adding how much? What is 2 power 9?
512.
Yeah, so you're adding 512 kilobytes. Right? So I am adding, for an 8 MB cache, I'm adding 512 kilobytes of overhead because you wanted to say you want to have a counter of 2 bytes. So,
So I think we can do it with lesser than that. I mean, I'm not sure, but
okay. So let's say, let's say I keep it 1 byte, right? Let's say I'm not happy with 2 bytes. Let's say I keep it with 1 byte.
yes,
I have 8 bits.
1 byte.
Okay. Let's say I will do 1 byte, which means that for an 8 MB cache, you are adding an overhead of 256, I think 256 kilobyte overhead you are adding. But I'm still okay. Let's say I keep it 1 byte. So what the Aditya is saying is, let's say he'll put the counter as 1 here. And then the CPU requested B1, B2, B3, B4, and then say B1 and then B2. Right. So then when he brings this, he will keep B2, then keep it here, then B3, then keep 1 here, then B4, then keep it 1 here. And then when the CPU generated a B1 request again, what he thinks he will do is he will replace this counter, he will increment this counter, he will make it 2. And then when B2 comes, he will increment this counter and make it 2. So that's what I think he would be doing. So now let's say the CPU generated an address, say B5, right? So he will look at these counters, whichever is the least, he will pick up. So now will you pick B3 or B4? Because these two both are
Sir,
least.
now we can implement least frequently used also in the same.
Okay, so you're saying I will use least recently used plus frequently used.
Yeah, both. Sorry.
So
Yeah.
okay, so you are saying I will implement both least recently used and least frequently used. So first I will pick the least frequently used guy, and then I will pick the least recently used guy.
Yes, sir.
Okay. Let's say. So do you think this will always do good? I mean, what? So does anybody want to say anything about this? So what happens if all the counters have reached 256? So let's say all the counter values have reached 256. Then what happens?
So do you need to know the total number of times something has been used, or you just need to know which is more than which?
Okay.
Like,
How do you know which is more than which?
every time you use something, you're
Mhm.
you're incrementing it, right? So instead
Yes.
of incrementing it, you can have like a sort of priority defined. So if you have 8 locations, I mean, you have 4 blocks here. So I have 1, 2, 3, 4. And whichever is used most frequently, I say that's priority 1.
Okay.
And in similarly 2, 3, and 4. So whenever I use something again,
Okay.
if it was not already priority 1, I put it. Oh, okay, you can't do that. I get it.
Okay, forget about this policy. I will ask you a very simple question. Let's see who answers this. How do I implement an LRE policy? I hope everybody followed. Forget about this new policy. Did everybody follow the least recently used policy? Just the least recently used. Forget about the new policy. The one that we said, this LRE policy. Did you follow the least recently used policy? The one that is least recently used is kicked out from the cache. Right? I mean, that's what generally everybody would come up with, right? So I see that I will look into the past. I will say, okay, the least recently used was, in this case, B2, because in the past, B2 has not been used. So I will remove this B2. Okay. So what I will do is to figure out what is least recently used. To figure out what is least recently used, let's say I have the CPU here. Right? I have 4 blocks here. I have stored B1 here, I have stored block 1 here, I have stored block 2 here, I have stored block 3 here, I have stored block 4 here. Now B5 came. Now, how do I figure out which is the least recently used among this? Can you tell me how do I figure out which is the least recently used in this 4?
Maybe, sir, here we can use that priority thing, which he said.
Yeah, but how do I use the priority thing?
If I access B1, then I will make it.
So now we are in the hardware. We don't have any software. I cannot have a priority queue and push the queue, top of the queue, pop the queue. I know that you are all data structure experts, but in hardware, what should I have extra?
Sir, we'll keep extra bits, sir, for remembering the.
Okay, so good. So what is the extra bit? How many bits do you need here?
So here we can keep 2 bits, like.
Okay, excellent. Okay, so now somebody is saying I'll keep 2 bits. Okay, let's keep 2 bits. So I have 0, 0, 0, 0, 0, 0, 0, 0. Okay. So I have 2 bits. Let's say the system has now started. There is nothing that is there. So we will see that this is always, the address stream is always B0, B1, B2, B3, and then B5 has come. Okay. So now B0 came. So what do you want to do? Just tell me, I will start doing that here. No, somebody said 2 bits, right? So what will you do next?
Sir, B0 is storing in first place, no, sir. So we'll keep it as 0, 0, sir.
Okay, so this is 0, 0. Okay, now B1 came. What should I do?
B1 will keep 0, 1.
So I will keep B1 here and write B0 1 here?
No, sir. We are using 2 bits, no, sir. If it's 0, 1, then we'll know that this is the second place, no, sir.
No, right? So you are using only 2 bits for the entire thing? For the entire cache, only 2 bits?
Sir, we have only 4 blocks, no, sir.
Okay, so no, I'm asking, do you want to have 4?
Sir, can we number like the order in which they enter? If B1 enters, we can write it as 1 and B0 as 2.
No,
like
you tell me I see your answers might be right. I want it in terms of the hardware. So what extra bits should I have? Where should I have those extra bits? Do you want to have
2
extra
bits for each block?
Okay, so let's go back to that, right? So let's say I have 2 bits for each block. Okay, now B0 came. So what do you want to do with that B0?
We will write 1, like 0, 1. In that
No, please tell me in the hardware. So where do I keep B0? Should I keep it here, or here? Yeah, anyway, all 4 locations are free. So where do you want to keep it?
Yeah, anywhere, just number 0, 1 below it.
Okay, good. So now what you are saying is I will make this 0, 1, right? Now, are you happy?
Yes.
Okay, so now B1 came. What should I do?
Here, I think we have to change B0 to 1, 0 and B1 to 0, 1.
Okay, excellent. So I write B1 here. So what you are saying is I will change this B0 value right? I will change this B0 value to 1, 0.
Oh, yeah.
Excellent. And then I will change this to 0,
0,
1.
1.
Excellent. Then I brought B2. What should I do?
This we have to change again for each and every block.
Okay. So now for B2, what you are saying is I will remove this. I will keep 1, 1 here. I will make 1, 0 here. This one 0, 1. Right? That's what you are saying. I will do.
Yes, sir.
Okay. So now what are you doing for every block access? For a single block access, you are actually changing all blocks counters, right?
Yeah, this is inefficient things.
I mean,
Sir,
this is not enough. This is impractical.
Sir, or else we'll just keep 0, 1, 2, 3, sir.
Okay, let's keep 0, 1, 2, 3. Okay, where do you want to?
And
keep
when we're
okay, no, before the before
Sir,
the
pushing-
no, wait. Is everybody convinced that this solution, though it works, though it comes up with an LRU policy, it is not possible for me to? I mean, of course, I can implement. But let's say I have a 32-way associative cache, then every time I'm accessing 32 blocks, I'm actually incrementing or decrementing or whatever for 32 counters, right? So which means that is an inefficient way of doing things, right? So
Sir.
it's okay.
Sir.
So is everybody convinced that this is not? I mean, though it gives me an LRU policy, it is not such great mechanism to implement. Is everybody convinced about it? So
Yes,
this will
sir.
come in your exam, right? And you might be thinking that LRU policy is simple. So we'll see as we go ahead in the class how simple it is. But yeah, see, if I had asked you to implement LRU policy in the software, you would have said, I mean, it's just a cakewalk, right? So it's just having one queue and pushing and popping out something, right? So, but yeah, okay. So now any other solutions? Anybody?
Sir,
wants go ahead.
Sir, we can have 2 bits universally.
Okay, 2 bits universal.
Since there are 4 blocks.
Okay, so this is universal bits now. Okay, so I have 0, 0. Okay.
So when B0 comes,
Okay, when B0 came,
it
so
sits on the first position.
okay.
So these 2 bits are set to 0, 0.
Yes, excellent. Then B1 came.
Then B1 comes and B1 goes in the second
Yes,
place.
excellent.
Then least recent would still be 0, 0.
Excellent. Then B2 came.
B2, B3 like.
B3. Then B5 came.
Yeah, then B5 comes. The least recent thing is 0,
Excellent.
0. So
Excellent.
replaces
So
B0.
Okay, excellent. So I replaced it with B5. Right?
So then now you increment 0 to 0.
No, how do you know that B1 was not accessed, right? Let's say B5
It is the least recently accessed, right?
No, right? Let's say, okay. Let's say this is not my access pattern. Let's say my access pattern was B0, B1, B2, B3, B1, B5, and then B6. Okay. So in your case, when B0 came, I would have kept B0 here. It was still 0, 0. Now you tell me B1 came, right? So this is my access. You will not do anything with this counter.
It is a hit, right?
Yeah, it's a hit. So you will not do anything with the counter.
Yeah.
Right, because you are still okay. Now B5 came, right? If B5 came, since 0, 0 is pointing to this, you are removing this and keeping B5. This is working perfectly fine. But when B6 came, you are saying since it is 0, 0, I will increment it. But B1 is already least recently used, right? See, the problem with your design is that you are only keeping track of the least recently used. But I should need the entire history, because once I remove the least recently used, I don't know what is the least recently used, right? Or LRU -1.
Okay, sir.
Yeah, this will not work. Any other?
We can put the data from the right side.
Okay, excellent. Okay, let's go there. Okay. So this also, I generally, sometimes HOD says don't ask these questions, but sometimes I ask them in the PhD questions. Yeah. Okay, so now what do you say? Where do I keep B0?
The rightmost one.
Okay, excellent. Okay, then?
Now when B1 comes, I shift B0 to left.
No, wait. Don't think like a software engineer. If I have to shift, what do you mean by shift in hardware? I have to read this. This is stuck in the hardware. So think about it as a hardware. This is a circuit. So B0 is stuck in the hardware. Now, if I have to shift here, you're thinking like a software engineer. But if I have to shift here, I have to read this data and then write it here, which means that for one single cache access, you are reading, writing, and then you are making again read. So for, let's say B0 came when B1 came. For B0, you did a write. For B1, you did a read, write, read. For B2, you not just did this, you did read, write, read, write, read. Sorry. For B3, you did read, write, read, write, read, write, write. Why are you doing this? Because you are shifting from here to here to here, right?
Yes, but can't we do like something like shift registers parallelly?
So, okay.
That also
right.
does this.
How many bits are there? Let's say it's a 64-byte block. How many bits are there?
64 byte into
No, 64 into 8, right?
8, yeah.
64 into 8 into 4. So how many bits are you shifting? And it's
11,
not just that
2
you
per
are,
level.
yeah, and also you have to shift the tags, right?
Yeah. Okay.
And you will only say don't implement it, right? I don't have to say that. Okay, now any other answers?
Sir,
Mm-hmm.
when the first instruction
Okay, so we'll start. Okay, so I mean, if you are not following, please let me know. But I mean, it's fun. I mean, it's like it's actually fun to figure out how to do this because it's, as I said, it's not straightforward. And we actually, the thing is, we are not even convinced. See, we are trying to break our head on this. We are not even convinced whether LRU is the right policy or not, right? So we are just saying out of experience that LRU is one of the good policies, and we are trying to implement LRU. First is our assumption is based on some shaky pillar saying that LRU is the best policy, and I'm trying to find out how do I implement it in the hardware. But we don't know whether LRU is the right policy because it might not be the right policy. Right? So I don't know. I mean, because I can't say it as a software engineer. I have to say it as an hardware engineer. I don't know whether it's right or not. So that's the first thing. So first, to figure out what is the right policy. Then when I figure out the right policy, I have to implement it in the hardware with as minimal hardware complexity as possible, which means that the amount of space, extra bits that I store, I can store hundreds of bits. But what is that which I use the extra bits? Keep the extra bits as minimal as possible. Keep the reads and writes as minimal as possible. So what somebody previously said the answer, right? It perfectly wise because what he's doing is he's just shifting it like a queue, right? So what happens when I push it to a queue? It just keeps pushing it to the previous one, right? So I mean, it works perfectly fine. But in hardware, it translates into equivalent reads and writes. So for everything, if I do that reads and writes, it's impossible to implement that. So you might have a good policy, but it might not be easily realizable in the hardware. So then you will have to come up with something where it is easily realizable. So there are two complexities now. One, to figure out a good replacement policy. One is to actually realize it in the hardware, thinking it in terms of the hardware itself. So that's why the answers are actually not really straightforward because we don't know like how to go about this, right? So that's why we have to figure out how to do this. The other okay. Anyway, we'll so try to follow this. If you are not following, please stop me. I will explain it to you. But the idea is just simple. That we have to figure out what is the least recently used block, kick out that block, and keep it with the assumption that the least recently used will not used. Now on top of this, Aditya is saying I will have LRU plus some whatever FRU or whatever, right? For what was it for frequently used, some other policies, right? So he came up with. So he said LRU plus LFU policy. We are not able to figure out an LRU policy, but now we want to tag along an LFU policy, which means that I'm just increasing the complexity, right? So what he said, 1 byte per block, an extra overhead of 256 kilobytes for an 8 MB cache. as on top of LRU. LRU itself has a complexity on its own. We haven't figured out how to implement an LRU. So by looking at it, finally you might conclude that the random policy is the best, because why break our head so much? So let's figure out. Okay, so somebody was saying answer.
Yes, sir. So there will be 2 extra bytes.
Extra bytes or bits?
Bits, sir. Sorry.
Okay, where should you keep this bits?
Outside and also near the 4 blocks also.
Oh, excellent. Okay, so I will have 2 bits here. So it's, let's say it is 0, 0, 0, 1, so 0, 0, 0, 0, 0, 0. And then you also have this one.
Yes, sir. Which contains the number of blocks filled.
It contains a number of blocks filled. Okay.
Yes,
Okay.
Okay.
Let's continue. So now B0 came. What should you do?
As the block number of blocks filled is 0, 0, it will be having the 0, 0 counter on near it.
No. What do I do? Do I keep it here?
B0 should be kept in the first block.
Okay. Then B1 came. What should
and
I do?
it should be incremented. 0, 0 should become 0, 1.
Okay. 0, 0 became 0, 1. Okay.
Not here, sir. Outside.
Okay.
Next B1 comes. So near the block B1 we should make into 0, 1.
Okay.
And the outside should be incremented to 1.
Okay.
And B3 comes.
B2 came.
Sorry, B2 comes and it will become 1, 0.
Why will it become 1, 0? Okay, so you are copying this.
Yes, sir.
Okay, excellent. Okay. Yes,
and that will become 1, 1.
Okay.
And the B3 comes 1, 1. And next this will be that will be same.
Okay, this will be same. Okay. Now B1 came. What will you do?
B5.
No, B1. I mean, anything can happen, right? So I just told B1 what to do.
Maybe we can directly go to the cache and search for B1.
Yeah, you'll search in the cache, but you will not increment or decrement or do anything about the counter.
No, sir, we won't do anything.
Then B0 came. You don't do anything about the counter.
No, sir. When B5 comes.
Yeah, so B5 comes, what will you do?
We will search for 0, 0 in the blocks. B0 has 0, 0.
But B0 came, right? So here B0 had come, right? So, but that is no longer the least recently used, right?
Oh, I forgot that case.
Yeah, it will not work.
Sir,
anybody?
Maybe we need not do the whole shifting operation for the values and addresses.
Okay.
But I can have the separate, like there are 4 blocks, right? So I can have 4 2 bits, like array of 2 bits, something like that.
No, it's not like that. You will have to have an address, then you have to have a pointer to the blocks, and then you have to shift. Think about it. We will take that in next one. Okay, so the NRU policy that I discussed was not recorded. So I will discuss the NRU policy again in the next class. It was not recorded. Okay. Yeah, so let's say there was no cache. I'm always accessing the main memory directly. The main memory takes 100 cycles. What is the average memory access time?
100 cycles.
100 cycles, right? 100 cycles. Now I don't have the. I directly don't go to the cache. Go to the main memory, but I go to the cache and then go to the main memory. Now my question is, what is the average memory access time? In total, if the CPU generates an address for the memory in total, or on average, when the CPU generates an address to be accessed or fetched from the, let's say the CPU generates an address. It is not worried whether you bring it from the cache or the main memory. It doesn't even know, maybe it doesn't even know that there is a cache. So it is just generated an address. What is the average cycles it will take for me to bring that block, give back that block to the cache? So we'll figure that out. Let's say I all 100% of, and this let's say takes 2 cycles. So cache access takes 2 cycles and main memory access takes 100 cycles. So this takes 2 cycles and this takes 100 cycles. And I, for some reason, I have designed a very efficient cache, and it always hits in the cache, which means that I don't have any compulsory misses, hold misses, conflict misses, capacity misses. I don't have any kind of miss. If I search for a block in the cache, the block is there in the cache. So now what is the average memory access time?
2 cycles.
2 cycles.
2 cycles, right? Now, instead of having 100% access time, I have 50% hit rate. So this is 100% hit rate. So this I am defining a new term. I'm telling you hit rate. What is hit rate of a cache? Hit rate is the number of accesses that were generated, and so I take the number of hits divided by number of cache accesses. So number of hits divided by number of cache accesses is hit rate.
Is number of cache accesses same as number of addresses generated by CPU?
Yes, for everything you go to the cache, right?
Okay.
For everything you go to the cache. So hit rate is number of hits divided by the number of cache accesses. Similarly, I have something called miss rate. Miss rate is number of misses divided by number of cache accesses. In this case, the miss rate is
0.
0, right? So miss rate is nothing but miss rate is nothing but 1 minus hit rate. Okay, so miss rate is nothing but 1 minus hit rate, right? So miss rate is nothing but 1 minus hit rate. So they are just additive complement of each other, right? So I have miss rate is equal to 1 minus hit rate. Hit rate is number of hits by number of cache accesses. Miss rate is number of misses by number of cache accesses. So if I don't have cache, the average memory access time was 100 cycles. If I have cache and I have 100% hit rate, the number of the average memory access time is just 2 cycles because everything is hitting in the cache. But if the hit rate is 50%, what is the average access time?
52 cycles.
How did you get 52 cycles?
Sir, if there are two cache accesses, one might in one we might get hit and in the other we can miss.
That's a good way of thinking. Any other answer? Okay, so we'll stop. 51. Oh, why is it 51?
If it's 50%, so whichever is not a hit is a miss, right?
Yes.
So,
but how did you get 1? Because this is 2 cycles and 50 cycles. How did you get 1 cycle?
Is it 100 cycles and 2 cycles?
Yes.
So half of 100 plus half of 2.
Yeah. So okay. I think that's what he also said. 52 cycles. But is there any other answer? Or I'm not saying you're wrong. I'm just trying to ask you.
Sir, here are we assuming that if it is a cache miss, then first data will be pushed into the cache and then it will be accessed to the...
No, I will directly give it to the CPU, so I don't have to push it in the cache. But when I search, see, these 2 cycles encapsulates everything. It just means when I'm searching, I have to pay the 2 cycle penalty. So that's the one formula that we'll continue. I will do a modification very late in the class, in the course, but we are assuming that it is taking 2 cycles. So when I search, it's taking 2 cycles. If it's a hit, then giving back to the CPU is encapsulated in the 2 cycles. But if it's a miss, I still pay the penalty of 2 cycles. So why they are saying it's at 52 cycles is, if there is an access that comes here, I pay 2 cycles. And if it's a miss, I go here and pay 100 cycles. So now for the first access, it was 102 cycles, right? That's what he came up with, 102 cycles. And when the second access came, it's maybe a hit in the cache. So I'm paying a penalty of 2 cycles. So average is 104 divided by 2. That's why they came up with the answer 52. Right? I think that's why you came up with the answer 52. Is that right?
Yes, sir.
Yeah, but I'm asking, can you come up with a general formula for this? So what happens if the hit rate is 30%? Yeah, just think about it. If you haven't understood this particular part of the class, then it's okay. I will be repeating it any time. Again, in the next class, we'll be again assuming that you don't know. I didn't discuss anything about this and then discuss.